question of whether we can travel at the speed of light touches on some of the most profound mysteries in all of physics. To truly understand why this cosmic speed limit exists, we need to venture into territory that most people never explore. Starting with something that sounds like pure science fiction, but is absolutely real. The quantum vacuum, what we think of as empty space, is actually teeming with activity at the smallest scales imaginable. Virtual particles constantly pop into existence and immediately annihilate each other, creating what physicists call quantum fluctuations. Under normal circumstances, these fluctuations average out to zero, and we never notice them. But something remarkable happens when you accelerate. There exists what scientists call the Unruh effect, a prediction that accelerating observers would perceive these quantum fluctuations not as virtual particles, but as real particles, creating a thermal bath of radiation around them. The acceleration needed to approach light speed would create what some physicists describe as a wall of quantum fire. This quantum fire would not just be uncomfortable, it would incinerate anything attempting to pass through it. The universe itself, at its most fundamental quantum level, seems to have built-in protection against light-speed travel. This is not a limitation of our technology or our engineering. This is the fabric of reality itself, pushing back against the very attempt. The discovery of the Higgs boson at the European Organization for Nuclear Research in 2012 opened another window into why light-speed travel faces fundamental barriers. The Higgs field permeates all of space, and particles acquire mass through their interaction with this field. Photons, particles of light, do not interact with the Higgs field at all, which is why they are massless and travel at light speed naturally. But everything with mass, including every atom in your body, is constantly interacting with the Higgs field. As you accelerate toward light speed, your increased kinetic energy means you are interacting more intensely with the Higgs field. This interaction becomes increasingly powerful as your velocity climbs, creating ever greater resistance. At light speed, this interaction would become infinite, an impossible state for any particle with mass. The universe has woven resistance into its very structure through the Higgs mechanism. From a computational perspective, the universe might be computing its own evolution, with light speed representing the maximum rate at which information can be processed. Think of reality as an unimaginably vast computer running a simulation of itself. Light speed would be equivalent to this cosmic computer's clock speed, the fundamental rate at which it can update from one state to the next. From this viewpoint, trying to exceed light speed would be like trying to make a computer run faster than its clock speed. Not just difficult, but literally meaningless. Every interaction between particles, every quantum state change, every moment of existence unfolds at a rate governed by this cosmic clock speed. Recent experiments with quantum computers have revealed that even these cutting-edge systems respect fundamental limits on information processing that trace back to light speed. The gravitational implications of approaching light speed reveal yet another layer of impossibility. According to general relativity, mass and energy curve spacetime. As an object's kinetic energy approaches infinity near light speed, its gravitational field would become increasingly intense. Some calculations suggest that at sufficient speeds, you could create gravitational effects comparable to a black hole. Imagine trying to travel between stars, only to have your own kinetic energy warp space around you so intensely that you create an event horizon, trapping yourself and everything nearby. The universe might prevent light speed travel simply to avoid these gravitational catastrophes. Every physical law seems designed to prevent the logical contradictions that would arise from breaking this cosmic speed limit. Something called the chronology protection conjecture, proposed by Stephen Hawking, suggests that the laws of physics conspire to prevent time travel on scales large enough to matter. Since faster-than-light travel would enable time travel, this conjecture implies that nature must forbid exceeding light speed through some mechanism. Hawking suggested that quantum effects would destroy any would-be time machine, creating infinite energy densities that prevent the formation of what physicists call closed time-like curves, paths through spacetime that loop back on themselves. Every loophole we find in the mathematics seems to come with a self-destruct mechanism built right into the physics. Studies of superfluids and superconductors have revealed that even exotic states of matter respect fundamental limits. In these materials, particles form collective quantum states with remarkable properties, zero viscosity, perfect conductivity, and other seemingly impossible behaviors. Yet even in these quantum materials, where matter behaves in its strangest ways, information and energy still cannot propagate faster than light. The speed limit holds even when we push matter to its most extreme quantum states. There appears to be no state of matter, no matter how exotic, that can bypass this fundamental constraint. Now let us explore what happens as you actually attempt to approach light speed. The journey toward this cosmic barrier transforms not just your motion, but the very nature of your existence. As you accelerate, something peculiar occurs that defies everyday experience. Your mass begins to increase, not your physical size or the amount of matter in your body, but your resistance to being pushed, what physicists call inertial mass. At 10% the speed of light, this effect is barely noticeable, just a tiny fraction of a percent increase. At 50% light speed, you become about 15% more massive. But at 90% the speed of light, your mass has more than doubled. As you creep closer, 99%, 99.9%, your mass skyrockets toward infinity. This is not just theoretical mathematics confined to textbooks. We observe this phenomenon every single day in particle accelerators. The Large Hadron Collider near Geneva accelerates protons to 99.99999% the speed of light. At these velocities, those tiny protons become 7,000 times more massive than when at rest. It takes the energy output of a small power plant just to nudge them that final tiny fraction closer to light speed. If we cannot get a single proton, one of the smallest particles in existence, to reach light speed with the most powerful machines ever built, how can we hope to accelerate a spacecraft weighing thousands of tons? The energy requirements scale in a way that makes even the grandest engineering dreams seem impossibly naive. To accelerate just 1 kilogram of matter to 99%, the speed of light would require energy equivalent to all the world's power generation for several years. To reach 99.9% would require orders of magnitude more. And to actually reach light speed would require infinite energy, not just an impractically large amount, but literally infinite. The universe has set up a mathematical wall that no amount of engineering cleverness can overcome. But mass increase is just the beginning of the weirdness that unfolds as you approach light speed. Time itself starts playing tricks on you. This phenomenon called time dilation means that as you travel faster, time passes more slowly for you compared to someone standing still. It sounds like pure science fiction, the kind of thing writers invent to make their stories more interesting. But it is verified reality, confirmed by countless experiments. The Global Positioning System satellites orbiting Earth have to account for this effect. Their clocks run faster than clocks on Earth's surface because they are moving at high speed relative to us. Without correcting for relativistic time dilation, the system would accumulate errors of about 10 kilometers per day. making navigation impossible. The implications become truly mind-boggling as you approach light speed. Imagine you are on a spacecraft traveling at 99.9% the speed of light to Proxima Centauri, our nearest star neighbor at 4.2 light-years away. From Earth's perspective, your journey would take just over 4 years. But on your spacecraft, due to time dilation, only about 60 days would pass. You would experience just 2 months, while Earth ages more than 4 years. Your friends and family would grow older by years, while you aged merely weeks. This is not some optical illusion or measurement artifact. Time genuinely passes differently for you. Your heartbeats, your thoughts, every biological and physical process in your body would run at normal speed from your perspective. But an outside observer would see you moving in extreme slow motion. Push even closer to light speed, and the effect becomes even more dramatic. At 99.99% light speed, time dilation increases by another factor of 10. That same journey to Proxima Centauri would feel like just 6 days to you, while over 4 years passed on Earth. At 99.999% light speed, it would feel like just 15 hours of travel time. From the photon's perspective, from light's own frame of reference, if such a thing could exist, no time passes at all. A photon emitted from a distant galaxy billions of light-years away experiences its entire journey across the vast cosmos in 0 time. From the photon's frame of reference, it exists at its point of emission and absorption simultaneously. This leads to a profound realization. Light speed is not just the speed of light. It is the speed of causality itself, the maximum rate at which cause and effect can propagate through the universe. It is the speed at which information travels, the speed at which anything can influence anything else. This is why nothing with mass can reach light speed. Reaching it would require experiencing 0 time, essentially existing outside of time itself, a state that makes no sense for anything that exists within the universe's causal structure. The relationship between space and time becomes even stranger at relativistic speeds. Einstein showed us that space and time are not separate entities, but aspects of a 4-dimensional continuum he called spacetime. When you move through space, you are also moving through time, and your total velocity through spacetime always equals the speed of light. This is a remarkable statement. When you are sitting still, not moving through space at all, you are moving through time at light speed, experiencing the normal flow of seconds, minutes, and hours. As you accelerate through space, you must move slower through time to maintain that constant space-time velocity. At light speed through space, you would stop moving through time entirely, a logical impossibility for anything that exists. This leads to one of the most mind-bending realizations in all of physics. Everything in the universe is always traveling at exactly the speed of light through space-time. Yes, you read that correctly. You, sitting wherever you are right now, are traveling at light speed. The difference is how that velocity is divided between the space dimensions and the time dimension. Massive objects like you mostly travel through time with little spatial motion. Photons travel entirely through space with no passage through time. This is not just a mathematical quirk or a clever way of describing things. This is the fundamental geometry of reality, the actual structure of the universe we inhabit. Space itself behaves strangely at high velocities. As you accelerate toward light speed, distances in your direction of travel begin to contract. This length contraction, also called Lorentz contraction, is just as real as time dilation. From your perspective on a spacecraft traveling at near light speed, the universe in your direction of travel literally becomes compressed. At 50% light speed, distances shrink to about 87% of their original length. At 90% light speed, everything is compressed to just 44%. At 99.9% light speed, the universe in front of you is squeezed down to less than 4.5% of its original depth. This means that the 4.24 light-year journey to Proxima Centauri would appear to be only about 0.19 light-years at 99.9% light speed. From your perspective, you are not traveling faster than light. Instead, the distance itself has shrunk. The universe has literally become smaller in your direction of travel. This effect has been confirmed experimentally. At the Stanford Linear Accelerator Center, physicists have observed that high-energy electrons behave exactly as if they are experiencing length contraction. When these electrons strike targets, the collision data only makes sense if we account for the fact that from the electron's perspective, the target has been compressed to a tiny fraction of its rest length. The visual experience of traveling at near light speed would be utterly unlike anything we can experience at normal velocities. Due to relativistic aberration, stars ahead of you would appear to crowd together. Light from stars to your sides would seem to come from ahead of you due to the extreme velocity. The universe would compress into an increasingly narrow cone in your direction of travel. At the same time, light would be blue, shifted in front of you, and red shifted behind you. Stars ahead would appear to glow with intense ultraviolet and even X-ray light, while stars behind would fade into dim red and infrared. The Doppler effect at these speeds becomes extreme. Just as a siren changes pitch as an ambulance passes you, light changes frequency when you move relative to its source. At 99.9% light speed, visible light from stars ahead would shift into the X-ray spectrum, while visible light from stars behind would shift into radio waves. The night sky would look completely alien, a bright glowing spot ahead, surrounded by darkness, with bizarre streaks and patterns unlike anything we see from Earth. This is not science fiction speculation. These are mathematical predictions from well-tested physics theories. Now, consider what happens if you try to communicate with Earth while traveling at these incredible speeds. You send a message back home describing what you see. From your perspective, traveling at 99.9% light speed, only 60 days pass on your journey to Proxima Centauri. But Earth experiences over 4 years passing during your trip. If you send a message every day from your perspective, Earth receives those messages spread over 4 years. Your daily updates arrive months apart, as measured by Earth clocks. The reverse is equally strange. If Earth sends you a message every day, you receive all those messages compressed. 4 years of messages arrive in just 60 days of your experience time. Time dilation does not just affect your biological aging. It affects every form of information transfer, every communication, every interaction between different reference frames. This creates profound practical challenges for any hypothetical near-light speed journey. Mission control on Earth cannot respond quickly to problems you encounter. By the time they receive your message describing an issue and send back a solution, months or years have passed on Earth, though only hours or days passed for you. You would be fundamentally on your own, isolated not just by distance, but by the structure of space-time itself. Any near-light-speed journey would require complete autonomy. The travelers would need to solve every problem themselves, with no hope of timely assistance from home. The energy considerations become even more daunting when we examine them in detail. Chemical rockets, like those that sent humans to the moon, are hopeless for relativistic travel. They simply cannot carry enough fuel. A chemical rocket trying to reach even 1% of light speed would require a fuel-to-payload ratio so extreme that no practical spacecraft could be built. Nuclear fission provides more energy per unit mass than chemical reactions, but still falls far short. Even nuclear fusion, combining hydrogen into helium, the process that powers the sun, struggles to provide sufficient energy for relativistic speeds. Matter-antimatter annihilation provides the highest energy density possible according to known physics. When matter and antimatter meet, they completely convert into energy, according to Einstein's famous equation: energy equals mass times the speed of light squared. This is the ultimate energy source allowed by physics. Yet even with perfect matter, antimatter annihilation, and perfect conversion of that energy into thrust, accelerating a spacecraft to 90% of light speed would require antimatter equal to roughly 40% of the ship's total mass. Where would we get thousands of tons of antimatter? Current annual antimatter production at all facilities on Earth amounts to mere nanograms, each nanogram requiring millions of dollars and enormous energy input to produce. Imagine scaling that up to produce the tons of antimatter needed for a relativistic spacecraft. It would require energy equivalent to the entire world's power generation for centuries. And we would need to somehow store this antimatter safely. Antimatter cannot touch normal matter, or it explodes with the most powerful chemical reaction possible. Any containment failure would result in an explosion making nuclear weapons look like firecrackers. A single kilogram of antimatter annihilating would release energy equivalent to 43 megatons, roughly equal to the most powerful nuclear weapon ever tested. Even if we somehow solved the energy problem, other challenges multiply. Interstellar space, which seems empty, actually contains about 1 hydrogen atom per cubic centimeter on average, along with dust grains and other particles. At everyday speeds, this presents no problem. But at 99.9% of light speed, even individual hydrogen atoms become deadly projectiles. When your spacecraft moving at near light speed strikes a stationary hydrogen atom, the relative velocity is so high that the collision energy becomes enormous. Each atom hits with the energy of a particle in a large accelerator, thousands of times more energetic than normal cosmic rays. A spacecraft traveling at this speed would constantly bombard its front surface with these high-energy particles. The cumulative effect would be like flying through a constant radiation storm. You would need massive shielding, probably several meters of dense material, just to protect against the interstellar medium. But this shielding adds mass, which requires more energy to accelerate, which requires more fuel, which adds more mass, creating a vicious cycle. Even with perfect efficiency and matter-antimatter annihilation, the engineering challenges multiply faster than the solutions. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, presents another unexpected hazard. This radiation is normally harmless, just faint microwaves at about 3 degrees above absolute zero. But from the perspective of a spacecraft traveling at 99.9% light speed, this radiation would be blue, shifted into high-energy gamma rays due to the extreme Doppler effect. Your spacecraft would be bathed in intense gamma radiation coming from the direction of travel. This radiation would add to the shielding requirements and create additional heating and structural stress. Even turning or changing direction becomes problematic at relativistic speeds. Your spacecraft has enormous momentum. The faster you go, the more energy you have invested in motion in a particular direction. Changing course requires applying force perpendicular to your motion, but at high velocities, the effective mass increases, making turns increasingly difficult. A gentle course correction that would take minutes at low speed might take days or weeks at near light speed, requiring sustained thrust and considerable energy expenditure. Navigation becomes a careful balance between your current trajectory and your desired destination, with any mistakes taking enormous time and energy to correct. Then there is the problem of stopping. Accelerating to 99.9% of light speed is only half the challenge. You also need to decelerate when you reach your destination. This requires just as much energy as the acceleration phase. Either you carry enough fuel to decelerate, doubling your fuel requirements, or you find some other method. Some proposals suggest using magnetic fields to push against the charged particles in space, creating a kind of magnetic sail for braking. But this only works if your destination has the right conditions, and the deceleration would take considerable time and distance. You cannot just slam on the brakes like in a car. The twin paradox illustrates another strange consequence of near light speed travel. If you have a twin who stays on Earth while you travel to a distant star at near light speed and return, you will have aged less than your twin. This is not just a thought experiment. It is a real effect. The traveling twin experiences less passage of time due to time dilation. When you return, you might be just a few years older, while your twin has aged decades. Families would be torn apart, not just by distance, but by time itself. A relativistic journey would mean saying goodbye to everyone you know, knowing that even if you return, they will have lived entire lifetimes, while you experienced just months or years. This raises profound philosophical and psychological questions. What would it be like to know that every decision to leave Earth at relativistic speed is effectively a one-way trip into the future? You could return to Earth physically, but the Earth you return to would be radically different. Friends would be old or dead. Society would have changed in ways you cannot predict. Technology, culture, politics, everything would have moved on without you. You would be a time traveler whether you wanted to be or not, perpetually out of sync with the world you left behind. Some physicists have explored whether there might be loopholes in these restrictions. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, suggests warping spacetime to move faster than light without actually exceeding light speed locally. The idea is to contract space in front of a spacecraft and expand it behind, creating a bubble that can move through space at any speed, even faster than light, while the spacecraft inside remains stationary relative to the bubble. Inside the bubble, you never accelerate and never experience relativistic effects. The bubble itself moves through space, carrying you along. It sounds like the perfect solution, but closer examination reveals devastating problems. First, creating the Alcubierre metric requires exotic matter with negative energy density. While quantum field theory suggests such matter might theoretically exist in tiny amounts under special conditions, we have never observed it in quantities larger than subatomic scales. Creating enough to warp spacetime around a spacecraft would require negative energy equivalent to the mass of a planet or star. We have no idea how to generate or manipulate such matter. Second, even if exotic matter exists, calculations show that quantum effects would likely destroy any warp bubble before it could form. The Alcubierre drive requires precise control over spacetime curvature on scales ranging from the microscopic to the macroscopic. Any instability would cause the bubble to collapse or explode, likely with catastrophic consequences. Some researchers have calculated that the energy densities involved might create a black hole or trigger other gravitational disasters. Third, the inside of the warp bubble would be causally disconnected from the outside universe. You could not see where you are going or communicate with the outside world while traveling. You would also have no way to steer or control the bubble from inside once it forms. You would need to program your destination before creating the bubble, then hope nothing goes wrong during the journey. If anything did go wrong, you would be helpless to respond. Fourth, The region of spacetime in front of the warp bubble would accumulate deadly high-energy particles during the journey. When the bubble stops and you try to exit, these particles would be released in a burst that could sterilize the destination. Imagine arriving at a star system only to destroy it with the cosmic ray burst from your own deceleration. Some calculations suggest the energy release could be comparable to a supernova in extreme cases. Finally, if warp drives were possible, they would enable time travel into the past, creating all the logical paradoxes associated with that. You could travel to a distant star faster than light, then travel back to Earth using conventional slower than light travel, but arrive before you left due to the relativity of simultaneity. This would allow you to meet yourself before you departed, creating a causal loop. Most physicists believe the universe must somehow forbid such paradoxes, suggesting that warp drives, even if mathematically possible, must be prevented by some mechanism we do not yet understand. Wormholes represent another theoretical possibility for effectively traveling faster than light without breaking the speed limit locally. A wormhole is a tunnel through spacetime, connecting two distant points. Instead of traveling the long way through normal space, you take a shortcut through the wormhole. General relativity allows such structures in its mathematics, but like the Alcubierre drive, creating and maintaining a wormhole requires exotic matter with negative energy. The throat of the wormhole must be held open against the natural tendency of spacetime to collapse it shut. Even if we could create a wormhole, there are severe limitations. The two ends of the wormhole must somehow be separated, which requires moving one end away from the other. But moving one end at high speed through normal space would create time dilation effects, turning the wormhole into a time machine. Again, we encounter the same causal paradoxes. The universe seems determined to prevent time travel, which suggests it must also prevent wormholes from being used for effective faster-than-light travel. Some researchers have proposed that quantum effects might create microscopic wormholes in the fabric of spacetime at the smallest scales, sometimes called quantum foam. These quantum wormholes would be far too small and short-lived to use for transportation, but they might play a role in quantum gravity. However, scaling from these hypothetical quantum fluctuations to human-sized wormholes requires extraordinary leaps in both technology and physics understanding. We would need to not just understand quantum gravity, but be able to engineer space-time itself at will. Tachyons are hypothetical particles that always move faster than light. Unlike normal particles that can never reach light speed, tachyons could never slow down below light speed. They would exist in a mirror universe of sorts where their physics is reversed. As a tachyon loses energy, it speeds up. To slow a tachyon down would require adding energy. But tachyons have never been observed, and their existence would likely violate causality, allowing effects to precede causes. Most physicists believe tachyons do not exist precisely because they would break the logical structure of the universe. Even if tachyons existed, using them for communication or travel would be problematic. A tachyon signal would arrive before it was sent from some reference frames. You could use tachyons to send messages into your own past. If you sent yourself a tachyon message telling yourself not to send the message, what happens? This is another version of the grandfather paradox from time travel. The mathematics of tachyons leads to contradictions, suggesting nature forbids their existence. String theory and other advanced physics frameworks have explored whether extra dimensions might provide routes to bypass the light speed limit. If our universe has additional spatial dimensions beyond the three we experience, perhaps we could travel through these extra dimensions, taking shortcuts through higher dimensional space. But string theory suggests these extra dimensions, if they exist, are curled up to incredibly tiny sizes, far smaller than atoms. Accessing them would require energies far beyond anything we can produce, and even if we could access extra dimensions, we would still be bound by light speed within those dimensions. The cosmic speed limit would apply in 10-dimensional space, just as it does in 3-dimensional space. Some popular science fiction employs what is called hyperspace, an alternate dimension where the speed of light is higher or does not apply. Ships jump into hyperspace, travel quickly, then jump back to normal space at their destination. But there is no evidence in physics for such a realm. All our observations suggest that space has 3 dimensions plus time, no matter how deeply we probe. The constants of nature appear to be truly constant across the entire observable universe. Light speed is the same in every location and direction we can measure. If hyperspace existed as a practical realm for travel, we would expect to see some evidence of it, some hint in astronomical observations or particle physics experiments. We see nothing of the kind. Each proposed loophole in the light speed limit has been explored thoroughly by physicists and has been found wanting. The universe seems to have anticipated every clever idea and built in protections against it. Whether through energy requirements, exotic matter needs, quantum instabilities, causal paradoxes, or gravitational disasters, every path to faster-than-light travel appears blocked. The more we learn about physics, the more robust the light speed barrier appears. Let us consider what we have actually achieved in space travel to understand how far we are from these theoretical limits. The fastest spacecraft humans have ever built is the Parker Solar Probe, launched in 2018 to study the Sun. As it swings around the Sun in its elliptical orbit, it reaches speeds of about 192 kilometers per second. That sounds impressive, but compared to light's 300,000 kilometers per second, Parker is crawling at just 0.065% of light speed. Even after decades of technological advancement, we are not even close to 1% of light speed. The Voyager 1 spacecraft, humanity's most distant ambassador, has been traveling for over 46 years and has reached a speed of about 17 kilometers per second. At this rate, it would take over 17,000 years just to travel 1 light year. The gulf between our current capabilities and light speed is not just large, it is almost incomprehensibly vast. Voyager is now in interstellar space, beyond the influence of the Sun's solar wind, but it is moving so slowly by cosmic standards that it will take tens of thousands of years to pass anywhere near another star. Nuclear pulse propulsion, proposed in the 1950s as Project Orion, would use nuclear explosions to push a spacecraft. By detonating nuclear bombs behind a massive shock absorber plate, the spacecraft would be accelerated by the explosions. This could theoretically reach a few percent of light speed, given enough bombs. But the technical and political challenges are enormous. The spacecraft would need to carry thousands of nuclear weapons. The vibrations and radiation would be extreme. International treaties now ban nuclear weapons in space. And even if we built such a craft, a few percent of light speed is still far from the relativistic realm where physics becomes truly strange. The concept of generation ships acknowledges the impossibility of rapid interstellar travel. If we cannot reach relativistic speeds, perhaps we should not try. Instead, build enormous spacecraft that can sustain human populations for centuries or millennia. Generations would be born, live, and die aboard the ship during the journey. Only their distant descendants would reach the destination. This avoids the physics problems of relativistic travel, but creates enormous engineering and social challenges. How do you build a closed ecosystem that can function perfectly for thousands of years? How do you maintain social cohesion and purpose across generations who will never see Earth or the destination? Some researchers have proposed using lasers or particle beams from solar system installations to push spacecraft equipped with light sails. The energy source stays at home, so the spacecraft does not need to carry fuel. A sufficiently powerful laser array might accelerate a small probe to 10 or 20% of light speed. But the laser array would need to be enormous, possibly hundreds or thousands of kilometers across, and would consume enormous amounts of power during the acceleration phase. The spacecraft would also have no way to decelerate at the destination unless another laser array was already there waiting, which seems impossible for the first mission. The Breakthrough Starshot project, announced in 2016, proposes using exactly this concept to send tiny spacecraft to Alpha Centauri, our nearest star system, at about 4.4 light-years away. Ultra-lightweight probes, perhaps just a few grams each, would be accelerated by ground-based lasers to 20% of light speed. At that velocity, they could reach Alpha Centauri in about 20 years. But these probes would be so small they could carry only minimal equipment, perhaps a simple camera and radio transmitter. They would flash past the star system at enormous speed, taking a few pictures, then continue into deep space, never to return. It is exploration, yes, but barely more than a reconnaissance photo. Even with these limitations, Breakthrough Starshot faces daunting challenges. The laser array would need to deliver about 100 gigawatts of power, focused on a target just meters across for a few minutes. Current laser technology falls far short of these requirements. The probes would need to survive the intense heating from laser light, and would need sophisticated miniature electronics that have not yet been developed. Any dust grain the probe encounters during flight at 20% of light speed would hit with the energy of a hand grenade, potentially destroying the craft. The project is more a research program to explore possibilities than a near-term mission plan. These various proposals and limitations show that even traveling at a modest fraction of light speed poses severe challenges with our current and near-future technology. True relativistic travel, approaching 50% or 90% of light speed, lies far beyond any realistic engineering project. And actual light-speed travel for massive objects remains not just difficult, but fundamentally impossible according to our best understanding of physics. The universe has set this boundary, and despite over a century of trying to find loopholes, every attempt has revealed that the boundary is more robust than we initially imagined. Yet there is something beautiful about these limits. The cosmic speed limit is not an arbitrary restriction placed on us by a capricious universe. It is deeply woven into the fabric of reality. Light speed, being finite and constant, is what makes causality work, what keeps causes preceding effects, what prevents the universe from descending into logical chaos. Without this speed limit, events could influence their own causes, effects could precede their causes, and the very notion of time would break down. The light speed limit ensures that the universe makes sense, that physics can predict outcomes, that science is possible at all. Consider what physics would be like if things could travel at any speed. There would be no maximum velocity, no fundamental timescale, no upper limit to how fast information could travel. This might sound liberating, but it would make the universe incomprehensible. Without a maximum speed, we could not have relativity, which means we could not have the relationship between energy and mass that powers the stars and makes chemistry work. We could not have quantum field theory, which describes all the fundamental forces and particles. The standard model of particle physics, one of the most successful theories in all of science, depends crucially on light speed being finite and constant. In a universe without a light speed limit, causality itself might not work properly. An event at one location could instantly affect an event at any distance. There would be no speed of light to limit how fast changes can propagate. But this would mean that the concept of distance itself becomes meaningless. If things can influence each other instantly across any distance, then in what sense are they separate? The notion of space as we understand it requires that influences take time to propagate. Light speed provides the conversion factor between space and time, the fundamental ratio that tells us how much time corresponds to how much space. The value of light speed, approximately 300 million meters per second, is not just a random number that happened to be the speed light moves. It is more fundamental than that. It is the conversion factor between space and time in the equations of physics. When we write equations describing motion, electromagnetism, gravity, or quantum mechanics, this number appears as the fundamental speed built into the structure of space-time itself. Changing this number would not just change how fast light moves, it would change the basic geometry of reality. Space and time would have a different relationship. Matter and energy would relate differently. Chemistry would work differently. Stars might not be able to shine. Atoms might not be stable. The universe would be unrecognizable. Every observation we have ever made confirms that light speed is constant, regardless of the observer's motion. Whether you are sitting still or moving at high velocity, you measure light moving at the same speed. This seems impossible at first. If you are on a train moving 50 kilometers per hour and you walk forward at 5 kilometers per hour relative to the train, someone on the ground sees you moving at 55 kilometers per hour. Velocities add in everyday experience, but light does not work this way. If you are on a spacecraft moving at 90% of light speed and you turn on a flashlight pointing forward, you do not measure the light moving away from you at 190% of light speed. You measure it moving at exactly light speed, 300,000 kilometers per second. And remarkably, someone watching from Earth also measures that light moving at exactly light speed relative to themselves, not at 190% of light speed. How can this be? How can light move at the same speed relative to everyone, regardless of their motion? This is where time dilation and length contraction come in. Time slows down, and space contracts in precisely the amounts needed to make light speed constant for all observers. The universe adjusts time and space themselves to preserve the constancy of light speed. This is not just a quirk of light or electromagnetism. It is a fundamental feature of space-time geometry. Maxwell's equations of electromagnetism were the first to reveal this, showing that light is an electromagnetic wave that propagates at a speed determined by the properties of space itself, not by the motion of the source. Einstein's insight was to recognize that Maxwell's equations were correct, and that our intuitions about space and time needed to change. Instead of assuming time flows at the same rate everywhere, and space has the same extent for everyone, he proposed that time and space are flexible, adjusting themselves to keep light speed constant. This might seem like an overly complicated way to describe things, but it is the only way to make sense of the experimental evidence. And once you accept it, a whole cascade of predictions follows, and every prediction has been confirmed by experiments. Particle accelerators provide daily confirmation of special relativity. At facilities like the Large Hadron Collider, CERN in Switzerland, Fermilab in Illinois, and many others around the world, particles are accelerated to velocities approaching light speed. These particles behave exactly as relativity predicts. Their masses increase, making them harder to accelerate further. Their lifetimes expand due to time dilation, allowing them to travel farther before decaying than would be possible at low speeds. Particle collisions produce energy distributions and particle production rates that match relativistic predictions precisely. In fact, particle accelerators could not function at all without accounting for relativity. The magnets that steer particles around the accelerator ring must be positioned and powered based on relativistic equations. If engineers tried to use classical Newtonian physics, the particles would crash into the walls of the accelerator immediately. Every successful acceleration of particles to high energy is a confirmation that relativity works, that light speed is indeed a fundamental limit, and that mass increases and time dilates exactly as the theory predicts. Cosmic ray observations provide another natural laboratory for testing relativistic effects. Cosmic rays are high-energy particles, mostly protons, that strike Earth's atmosphere from space. When these particles hit air molecules high in the atmosphere, they create showers of secondary particles, including particles called muons. Muons are unstable, decaying with a half-life of about 2 microseconds. At light speed, a muon should travel about 600 meters before half of them decay. Yet we detect muons created 20 kilometers high in the atmosphere reaching sea level. How is this possible? Time dilation. From the muon's perspective, racing through the atmosphere, at 99.98% of light speed, time passes much more slowly. Its 2 microsecond half-life becomes 30 microseconds or more in Earth's reference frame, giving it time to reach the surface. Without time dilation, we would detect almost no muons at sea level. But we detect them in abundance, exactly as relativity predicts. Binary pulsar systems offer yet another test of relativity, this time involving gravity. A pulsar is a rapidly spinning neutron star that emits beams of radio waves. When 2 pulsars orbit each other, they form a binary system where we can measure orbital changes with extraordinary precision. According to general relativity, these orbiting massive objects should emit gravitational waves, ripples in spacetime itself, that carry energy away from the system. This should cause the orbits to gradually decay, with the 2 stars spiraling closer together. The rate of this orbital decay can be calculated precisely using Einstein's equations, and the observations match the predictions perfectly, providing strong evidence that general relativity correctly describes how space-time works, and confirming that gravitational waves travel at light speed. The detection of gravitational waves directly by the laser interferometer, Gravitational Wave Observatory, usually abbreviated as LIGO, and other gravitational wave detectors, represents another triumph of relativity. These facilities detected ripples in spacetime caused by colliding black holes and neutron stars. The waves traveled across the universe at light speed, arriving at Earth as predicted by general relativity. The wave patterns matched theoretical predictions based on Einstein's equations. The energy carried by these waves, the frequency evolution, the polarization, everything matched. Gravitational waves could not exist in Newtonian physics. They are a unique prediction of general relativity. Their detection confirms that space-time is a real physical thing that can ripple and wave, and that these ripples propagate at exactly light speed. Astronomy provides countless other confirmations. The light travel time delay from distant objects, the way massive objects bend light gravitationally, the expansion of the universe, the cosmic microwave background radiation, the formation and evolution of galaxies. All of these phenomena are understood through relativity. Light from the most distant galaxies has been traveling for over 13 billion years to reach us. The light we see left those galaxies when the universe was young. We are seeing the past because light takes time to travel. This finite light speed gives us a window into cosmic history. The expansion of the universe discovered by Edwin Hubble in the 1920s, shows that distant galaxies are moving away from us. The farther away a galaxy is, the faster it recedes. At sufficient distances, galaxies recede faster than light speed. Wait, does this not violate the cosmic speed limit? No, because the galaxies are not moving through space faster than light. Space itself is expanding, carrying the galaxies along. There is no local violation of light speed. Each galaxy is at rest in its local patch of space. The distance between patches is increasing because space itself grows. This distinction is crucial. Light speed limits motion through space, but space itself can expand at any rate. In fact, inflation theory suggests that in the first tiny fraction of a second after the Big Bang, space expanded vastly faster than light speed, growing from smaller than an atom to larger than our solar system in an unimaginably brief instant. Black holes represent the ultimate gravitational consequence of relativity. When matter collapses to sufficient density, it warps spacetime so severely that a region forms from which nothing, not even light, can escape. The boundary of this region is called the event horizon. At the event horizon, the escape velocity equals light speed. Anything crossing the horizon is trapped forever because it would need to exceed light speed to escape, which is impossible. Inside the event horizon, all paths through spacetime lead toward the center, toward the singularity. Time and space exchange roles, in a sense. Just as you cannot avoid moving forward in time outside a black hole, you cannot avoid moving toward the singularity once inside. Black holes have been observed indirectly through their effects on surrounding matter for decades. Matter falling into a black hole forms an accretion disk, a swirling disk of superheated material that emits intense radiation just before crossing the event horizon. We have observed these accretion disks around many black holes. We have measured the orbits of stars around the supermassive black hole at the center of our galaxy. These stars move at thousands of kilometers per second in their elliptical orbits, confirming the immense mass concentrated in a tiny volume. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, showing the dark region where light cannot escape surrounded by the glowing accretion disk. This image matched predictions from general relativity with remarkable precision. Hawking radiation, a theoretical prediction by Stephen Hawking, suggests that black holes can actually emit radiation and slowly evaporate over enormous timescales. This radiation arises from quantum effects near the event horizon. Virtual particle pairs created by quantum fluctuations near the horizon can be separated by the intense gravitational field, with one particle escaping while the other falls in. This causes the black hole to lose mass slowly. For typical black holes, this process is extraordinarily slow, taking longer than the current age of the universe. But for very small black holes, if they exist, Hawking radiation could be significant. This theoretical prediction connects quantum mechanics, general relativity, and thermodynamics in profound ways, hinting at the deeper structure of reality that we do not yet fully understand. Quantum mechanics introduces additional subtleties to the story of light speed. Quantum field theory, which merges quantum mechanics with special relativity, shows that particles are excitations of underlying quantum fields. Photons are excitations of the electromagnetic field. Electrons are excitations of the electron field. Each type of particle has its own quantum field permeating all of space. These fields interact according to rules governed by both quantum mechanics and relativity. Light speed appears in these equations as the maximum speed at which information can propagate through the fields. Quantum entanglement, where two particles share a quantum state, such that measuring one instantly affects the other regardless of distance, seems at first to violate the light speed limit. Einstein famously called this spooky action at a distance and was troubled by it. But careful analysis shows that entanglement cannot be used to send information faster than light. When you measure one particle of an entangled pair, the result appears random to you. The correlation with the other particle's measurement is only revealed when the two sets of measurement results are brought together and compared, which requires transmitting information at light speed or slower through normal channels. Entanglement is real and has been confirmed by countless experiments, but it does not violate causality or allow faster than light communication. The no-cloning theorem in quantum mechanics, which states that you cannot create an identical copy of an unknown quantum state, is related to the light speed limit. If you could clone quantum states, you could use entanglement to send messages faster than light, creating causal paradoxes. The structure of quantum mechanics forbids this through the no-cloning theorem. Again, the universe seems to have internal consistency checks built in at the deepest level, preventing any mechanism that would allow faster than light information transfer. Quantum tunneling, where particles can pass through energy barriers that classical physics says they should not be able to penetrate, also seems to involve faster than light motion in some sense. A particle tunneling through a barrier appears on the other side without having traversed the space between, at least not in the classical sense. Some experiments have measured the time taken for tunneling and concluded that it appears instantaneous. But again, careful analysis shows that you cannot use tunneling to send information faster than light. The tunneling probability depends on the properties of the barrier and the particle, and measuring whether a particle has tunneled reveals information that was already encoded in the quantum state, not new information sent faster than light. These quantum phenomena show that reality at its deepest level is far stranger than everyday experience suggests. Particles are not little billiard balls following definite paths. They are quantum entities described by wave functions that encode probabilities. They can be in superpositions of states, existing in multiple states simultaneously until measured. They can be entangled with other particles, sharing quantum states across vast distances. They can tunnel through barriers, appearing on the other side without classically traveling through the middle. Yet through all this quantum weirdness, the light speed limit holds. No information, no causality, no influence propagates faster than light. The quantum world is bizarre, but it respects this fundamental constraint. The development of quantum computing in recent decades has explored the limits of information processing. Quantum computers use quantum superposition and entanglement to perform certain calculations much faster than classical computers. But even quantum computers cannot violate the light speed limit. The speed at which quantum gates can be operated is limited by light speed. Information transfer between quantum bits happens at light speed or slower. A quantum computer is not a magical device that can do anything. It is bound by the same physical laws as everything else, including the cosmic speed limit. Experiments in quantum teleportation successfully transfer quantum states from one location to another using entanglement and classical communication. But the name is misleading. Nothing actually travels faster than light. The quantum state information is essentially disassembled at one location. Classical information about the disassembly is sent at light speed or slower to another location, and the state is reassembled there using entanglement. It is a remarkable phenomenon, but it does not enable faster than light travel or communication. It is more like a quantum fax machine than Star Trek-style teleportation. The holographic principle, arising from studies of black hole thermodynamics and quantum gravity suggest that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram. This principle has profound implications for how we understand space and reality. It suggests that three-dimensional space might be a kind of projection from information encoded on a two-dimensional surface. But even in holographic theories, the light speed limit remains. Information cannot propagate faster than light through the holographic surface or through the emergent three-dimensional space. String theory, perhaps the most ambitious attempt to unify quantum mechanics and general relativity, proposes that fundamental particles are not point-like, but are tiny vibrating strings of energy. Different vibration modes correspond to different particles. String theory requires additional spatial dimensions beyond the three we experience, curled up to microscopic size. These extra dimensions might explain aspects of particle physics and gravity that are mysterious in conventional theories. But string theory does not eliminate the light speed limit. In fact, string theory is built on special relativity and incorporates light speed as a fundamental parameter. Any predictions string theory makes about our universe must respect relativistic constraints. Loop quantum gravity, another approach to quantum gravity, suggests that spacetime itself is quantized at the smallest scales, coming in discrete chunks rather than being continuous. Just as matter is made of atoms and energy comes in discrete quanta, spacetime might have a granular structure at the Planck scale, about 10 to the minus 35 meters. At this scale, classical concepts of smooth spacetime break down. But even if spacetime is quantized, the light speed limit should still hold as an average or effective limit over larger distances. The discrete structure of spacetime, if it exists, would not provide a loophole around the cosmic speed limit. All these theoretical frameworks and experimental results point to the same conclusion. The light speed limit is not just a feature of electromagnetism or a consequence of how light moves. It is a fundamental feature of spacetime geometry, woven into the very structure of reality at every level. Whether we look at classical relativity, quantum mechanics, particle physics, cosmology, black holes, or speculative theories of quantum gravity, we find the same constraint appearing over and over. The universe has one set of consistent laws, and those laws impose a maximum speed for causality. After over a century of exploring these ideas, testing them experimentally, and searching for loopholes, the scientific consensus is clear. Light speed travel is impossible for anything with mass. You can approach light speed arbitrarily closely, at least in principle, but you can never reach it. The closer you get, the more energy is required for each additional increment of speed. At the limit, infinite energy would be required, which is obviously impossible. Even if you somehow obtained infinite energy, the other problems, mass increasing to infinity, time dilation to zero, length contraction to zero, all prevent the possibility of actually reaching light speed. But there is something poetic about reaching toward the impossible. Humanity has always been characterized by a drive to explore, to push boundaries, to see what lies beyond the horizon. The light speed limit tells us that there are genuine horizons in the universe, boundaries we cannot cross. The observable universe has a finite radius, currently about 46 billion light-years, beyond which light has not had time to reach us since the Big Bang. As the universe expands, this horizon moves outward, but there are galaxies currently beyond our horizon that we will never be able to reach, even in principle, because space between us and them is expanding faster than light. We can see some of them now, because the light that left them long ago is just reaching us. But if we tried to travel to them, we would never arrive. The universe is larger than the part we can access, and that boundary is set by light speed. Within our observable universe, there are billions of galaxies, each containing billions of stars. Many of those stars have planets. Some of those planets might harbor life. Some might have civilizations asking the same questions we are asking. But the vast distances and the light speed limit ensure that communication with such civilizations, if they exist, would be extraordinarily difficult. A radio signal sent to a star 1,000 light-years away would take 1,000 years to arrive. A reply would take another 1,000 years to return. Any conversation would span millennia. Any exchange of ideas would involve many generations on both ends. And that assumes both civilizations remain stable and interested for that entire time, which seems improbable given human history. This isolation might seem depressing, but it also means that life throughout the universe can develop independently, producing incredible diversity. Different evolutionary paths, different biochemistries, different solutions to the challenges of existence, all developing in isolation, unable to interfere with each other until they reach advanced technological maturity. The light speed limit protects young civilizations from premature contact with more advanced ones. It ensures that each world has time to develop on its own terms. It creates a cosmos rich with possibility, where countless independent experiments in life and intelligence play out simultaneously across billions of worlds. For humanity, the light speed limit means that interstellar travel, if we ever achieve it, will be a slow, patient process. Generation ships or hibernation might allow journeys to nearby stars. We might send robotic probes that report back across decades or centuries. We might eventually establish colonies on other worlds, but those colonies would be largely independent due to the communication delays. Each world would develop its own culture, its own approach to challenges, its own identity. Humanity might spread through the galaxy over thousands or millions of years, but we would become not one species, but a family of related species, each adapted to their own world, each with their own history. There is grandeur in this view of the cosmos, a universe so vast that light takes billions of years to cross it, a universe where every location has its own local now, its own present moment, with no universal simultaneity, a universe where the past, present, and future are relative concepts depending on your motion, a universe where space and time are flexible, adjusting themselves to preserve the constancy of light speed and the integrity of causality, a universe that operates according to comprehensible mathematical laws, but whose implications are far stranger than our everyday experience prepares us for. Thank you for joining me on this exploration of why light speed travel is impossible. I hope you have found it thought-provoking and perhaps even comforting. The universe has rules, and those rules create a structure, a framework within which existence unfolds. Light speed is not a frustrating limitation arbitrarily imposed to thwart our ambitions. It is a necessary feature that makes the universe logical, predictable, and beautiful. It ensures that causes precede effects, that science is possible, that reality makes sense. In understanding why we cannot travel at light speed, we come to understand something profound about the nature of existence itself.